Hello, and welcome to Chapter 4, Section 4. I'm splitting this section into two parts because there's some pretty important stuff in here. So, Part 1, the fundamental theorem of calculus. So, this is probably like the most important part of this chapter. Not the most difficult, definitely not the most difficult. Pretty straightforward, but important. So here we go. Fundamental theorem of calculus is for when we are trying to evaluate integrals, where we have specific endpoints. So we're used to seeing, the integral sign, and then we have endpoints from a to b. So this is our definite integrals, because there's endpoints, of some function f of x dx. So in order to evaluate this, in the past section, all we did was kind of just be able to write it out. We could use the different shapes like rectangles, triangles to actually figure out that area underneath f of x. But now let's actually do this without graphing it first. So in order to find this definite integral, or to evaluate this definite integral, we want to find the antiderivative, the integral of f of x, and we are used to using capital F to stand for this. So the antiderivative of regular f of x would be capital F of x. And then, once you've found it, plug in b and subtract the antiderivative when you plug in a. And that's it. So you're finding antiderivatives, plugging in your endpoints in for x, and then solving from there. Let's do examples. All right, so our first example is going to be the integral from 1 to 2. So those are our endpoints of x squared minus 6 dx. So graphically, what we're doing is like graphing the x squared minus 6 and then looking at the area underneath that curve between x values of 1 and 2. So that's what we're trying to figure out with this notation, but we just don't want to graph it because, why spend more effort? So what we were saying with the fundamental theorem of calculus was to find the antiderivative of x squared minus 6 and then plug in our endpoints of 1 and 2 and subtract. So x squared minus 6, we can use the power rule to find the antiderivative. So with x squared, we would get x cubed over 3. With the minus 6, it would end up being minus 6x. So there's our antiderivative. And then the notation, I'm not super worried about it, but this is how we usually write it in math. If my endpoints were to take the integral from 1 to 2, I just do like a little square bracket around my antiderivative and then put 1 to 2 next to it because those are my endpoints. And then from here, we always start with the bigger number, so 2. Plug in your 2 into all the x's that you see. So that's what I get from plugging in 2, and we're subtracting it from me plugging in x equals 1 now as my other endpoint in for x. So it'd be 1 cubed over 3 minus 6 times 1. And then from here, we just need to simplify this out. So after I simplified, I'm just going to take away the parentheses and kind of combine my like terms-ish, get a common denominator. So I end up with negative 11 over 3. And if you remember, a negative area just means most of your graph was underneath the x-axis, which is fine. So this is our antiderivative with our endpoints plugged in. So if we were to graph this out, the area would end up being negative 11 over 3. Let's do another example. So this time let's take the integral from 1 to 4 of 2 square root x dx. So same thing, let's just find the antiderivative of 2 square root x first. So 2 square root x, if I want to use the power rule, this is really 2x to the 1/2 power. So the 2 is just a constant, I can put that in front. X to the 1/2 would become x to the 3 over 2 by adding 1 to the exponent, and then divided by 3 over 2 as the power rule. And then let me just simplify this out to make it look a little bit nicer, because if I'm dividing by 3 over 2, this is the same as multiplying by 2 over 3. And that 2, whether it's inside or outside the parentheses, it actually doesn't matter, because either way you're going to have to multiply it out by the 2. So let's start plugging stuff in. 2 times 2 over 3 is just 4 over 3. 4 to the 3 over 2 power, and then minus 4 over 3 times 1 to the 3 over 2 power. And if you're not too familiar with our exponents that are fractions, this is just a square root, so whatever the denominator is, that's the index of your radical. So this is a square root raised to the 3rd power. So if you want to think about it as the square root of 4 raised to the 3rd power minus the square root of 1 raised to the 3rd power so we end up with, after simplifying it all out, 28 over 3. So that'll be the area under the curve from x equals 1 to x equals 4 of the curve to square root x. Alright, let's do an example with some trig. So this time we are finding the integral from pi over 4 to 3 pi over 4 of cosecant squared x dx. Okay, so first, find the antiderivative. So the thing that I can take a derivative of to get cosecant squared x would be negative cotangent x. Because cotangent, the derivative of cotangent is negative cosecant squared. So if I do the negative cotangent, then its derivative would be cosecant squared. Okay, so now I just need to plug in my endpoints of pi over 4 and 3 pi over 4. Cotangent is really just 1 over tan. So tangent of 3 pi over 4 is negative 1. 1 over that would be negative 1. So a negative of that would be a positive 1. Oh boy, there were a lot of negatives there. Okay, then minus cotangent of pi over 4 would be 1 over tangent of pi over 4. Tangent of pi over 4 is positive 1. Negative of that would be negative 1, so minus a negative 1. So I end up with 1 plus 1 equals 2. Cool. So that would be the integral from pi over 4 to 3 pi over 4 of cosecant squared x. All right, last example. This time we are looking for the integral from 1 to 3 of 5 to the x power dx. All right, so same process again. Let's find the antiderivative of 5 to the x power, and then plug in our endpoints of 1 and 3, and then subtract. So the antiderivative of 5 to the x is a little awkward because we can't use the power rule here since our exponent is actually x and not like a number. So we can't use the power rule here, but if you remember your derivatives, the derivative of 5 to the x power is natural log of 5 times 5 to the x. So the derivative itself already has a 5 to the x in it. So now we're basically asking ourselves, what can I take the derivative of where my answer, the derivative, is just 5 to the x? And if you think about it this way, if I take 1 over natural log of 5 times 5 to the x, if I were to take the derivative of this, 1 over natural log of 5 is just a constant because there's no x's in it, it's just numbers. Natural log of 5 is just a decimal. So 1 over natural log of 5 is just a constant, so that would stay in front when we take the derivative because that's a constant multiplier. Then the derivative of 5 to the x would be this, the natural log 5 times 5 to the x. And so multiplying that out with the 1 over natural log of 5 would cancel out and leave me with just 5 to the x, which is what I wanted. So this is the antiderivative of 5 to the x. So using this, we're plugging in 1 to 3 as our endpoints, and then subtracting. So I'll write this out as 5 cubed is 125 over natural log of 5 minus 5 to the first is just 5 over natural log of 5. Since I have common denominators, I can just subtract the top. So I end up with 120 over natural log of 5. And that's it. If you really wanted, you can find this as a decimal, because that would make a little bit more sense in terms of area under the curve, but this is fine if we just leave it like this. It's fully simplified. All right, that's it for part 1 of this section. See you next time. Don't forget to like and subscribe. Bye.